Okay, good afternoon. Um, I'm here to present the proposal, and as was said in the introduction, the idea here is to improve turnaround time, okay, and that will give great benefits, but there will be also a few other things which can create a lot of market, okay. So this has been developed at one of the Tier 1 centers for the LHC, which is my center, PIC. Curiously enough, it turns out that the phrase, which is 10 years old, which is our lemma, helping to turn information into knowledge, was used in one of the previous presentations. So it sort of struck me. Yeah. So I guess this is a good thing. Really the people who have done this work are Dr. Yolanda Vives and engineer Jordi Delgado. Yolanda couldn't come because she's nursing, and Jordi is actually at a neuroimaging meeting in Amsterdam, which happened to fall on the same day. So the boss had to come to present it. So a brief introduction so that it's understandable what we're trying to do. There is a whole area of medical research, both academic and industrial, mainly done by pharmaceutical companies, which greatly benefits from the results of medical imaging, either through magnetic resonance or through positron emission tomography, in order to study particularly neurodegenerative diseases. You all know that, for example, Alzheimer's, but also other diseases which are perhaps more rare, like Huntington disease, have become very, very important. Now, as compared to the sort of more known use cases like have been presented, like high energy physics or molecular biology or space, the typical doctor researcher, as I call them, okay, is not interested in computing at all. Okay, in fact, they are interested in their science, and computing is somehow some sort of plumbing that they're not interested in. And however, to let's say service these doctor researchers is not at all easy. You know, just understanding what they're saying to you is sometimes not easy. Okay? So you need sort of this crew, these sort of intermediaries, which I've called for this presentation the technician researchers. Okay, who are people with university studies, sometimes even doctorates. Okay, often in the current scenarios, they are actually graduate students. Okay. That do this job, okay? And the typical environment is that they present a project and they get a lot of money for supporting graduate students or hiring these technician researchers, and then they say, and by the way, we need a couple of PCs, and they put them somewhere under the desk of the hospital, okay, and they run these jobs sequentially. And this severely limits, actually, the kind of research that they do. Okay. However, as is many times the case, someone from outside has to come and tell them that, because, you know, you often don't see the truth when you look in the mirror, okay? So the key factor in accelerating this research is turnaround time, and evidently clusters, grids, or clouds could help here, with each one with pluses or minuses. So the scientific objective of what we're trying to accelerate is to improve the speed. The official name of this are called surrogate biomarkers. This means that these are biomarkers that you can do without actually slicing the person into pieces. Okay, so you actually, this is the nice thing about imaging, is that you don't damage the person. Okay, and basically there are two fields. They're the earlier and earlier detection of neurodegenerative diseases. You may have heard that, you know, there is now some evidence that even people with 30-something years of age are showing some signs of Alzheimer's if you can detect them. Okay, and this has to be then somehow verified through some physiological effect. Okay, so for example, the hippocampus surface gets wrinkled. Okay, and you need to statistically prove this. So this is science. Okay, of course, you also want to check, and this is very important, that if you give somebody maybe with a more advanced stage of the disease some pharmaceutical that you're developing, that the pharmaceutical actually does something, okay? Now, often this is done, for example, through some memory test and so on. But of course, if you can show that actually this wrinkling of the hippocampus surface has been reversed, okay, then this is very important. Okay. So, the technological vehicle is what we've been working on for the last 8 years, which is a web-based platform, which in some sense is very similar to what some other things that have been presented. It's somehow the easy-to-use window into the speed up of the computing, okay? And get away from the graduate students submitting one job a day in the PC under the desk. Okay. Now, the idea of the flagship is of course, surprise, surprise, to put a backend on the cloud, okay, for this. Now, let me just very quickly see how I'm doing on time. Yeah, very quickly go through. So we call this thing PICNIC, okay, PIC Neuroimaging Center, okay. The funny thing about it is it's so hard to get data out of hospitals, even if it's research data, that in some sense we tell them that they have to come with a basket to have a picnic with us, you know, and bring their data. Sometimes it's so hard to get the data out of the hospital that hard disks in the picnic basket is the only way that the data can come out. Okay? No, don't tell them I said that. Okay. So basically, there are some components. The main one component is to be able to upload the data and to make sure that the data is checked, because of course there's a series of issues about, you know, that you shouldn't be sending images around which say whose image it is. Even today, people have realized that even a scanner, if you use the right software, you can actually reconstruct the face of the person. So you could actually, without any information, just reconstruct it, you could actually identify somebody. So in fact, sometimes the area of the face, if it's not important for the research, is somehow blurred, and so on. So there's this whole process of data acquisition. I should say it's not formally part of the picnic, but I'm so proud of it that you know, I have to say it. We actually even have interfaced one scanner, which is in a hospital, where by miracle the research network is very nearby. It's in the building just next door. So we've actually interfaced it, and we're actually running, and Steve, if he's here, he will like this, we're actually running an FTS channel, okay? So the same technique that we use to bring data from the LHC, we actually use it to actually upload data from the scanner. It's of course killing, as we say in Spain, killing flies with a machine gun, okay? Because the data rate is very small, but what they like is the automation, okay? They just put it there and it appears there, okay? Then there's the processing itself, and then, of course, the doctor really is not interested in computing, but is very interested in the results. So then there is a visualization phase, and often there is a statistical analysis phase where we also provide some support. And the whole idea, as you see, is that when you enter, for example, you actually go and very easily choose, you know, if you want to know how the jobs are running, this and that. It's a very clean interface, okay? Whoops. Actually, it was mentioned in one of the earlier presentations that it's very important, the user interface. Okay, so what happens is somebody was asking me during the break. There's something like 6 to 8 packages which are very much used, and these come from places like MIT, like Oxford, Cambridge, and various other places. Usually, there is a kind of a free-to-use version for research, okay, which is kind of the latest version. And then there is an older version, which is typically 2 years old, which is very, very expensive, because this is the one that is actually approved by the FDA or the similar bodies for clinical, okay? So we need to differentiate between those two things. The doctors always want to use the latest one, okay? And if they could, they would use it even for clinical, because it's usually better, okay? But, and now what we do is we put a face on this, which these innocent little flashes here are each one for one of the different products. But what's behind the scene is that you've actually said, okay, I'm uploading some data, and now I'm going to process it with one of these tools. Let's take FSL. This is the Oxford Cambridge, I believe. Okay. And so you need to put some parameters, you need to decide. But behind the scene, the moment you have said, I'm going to process it with this, the raw data and the auxiliary data, if there is any, has actually been put into all of the directory structures that the Unix scripts that run this software, okay, and that the doctors have no idea how to use, okay, everything has been put into its place because, of course, it's been programmed. That's why it took us 4 years to develop. First of all, we needed to talk to the doctor, see what they wanted, and then actually program it in. So there's a lot of value in this interface, okay? And then the other thing is that this, you may say, well, you put a pretty face on a program, so what? But when you push go, it doesn't submit one image, it submits a whole data set. And it monitors the jobs, and it monitors where all the outputs are going, et cetera, et cetera. Okay, so this is the sort of value added. And it's homogeneous in the sense that, I mean, each one is different, evidently, because the parameters are different. But let's say a technician researcher can come here and say, okay, now this guy asked me for the MIT software. Click. Okay, what do I have to fill in here? Boom, 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 submit. Okay, and so it increases productivity. Okay. Now, what's behind is a kind of standard technology, if you wish. Okay, it's a series of, I mean, in some sense, we also put together various tools, as was mentioned earlier. But the main thing is an uploader for data, interface to the cluster, tools for image format conversion, and all of these things are maybe different. Some stuff is in Java, some stuff is in Python, some stuff is C++, etc. Also there is a database, but this is mostly for the auxiliary data. You need to know the gender, the age, and so on of these brain scanners. And there is it talks to the world through web. Okay. Now what happens here is that here is the tier 1 cluster. Okay. But there is actually some other nodes, because we started having problems immediately, because when we said, oh, this has to run on Linux 5.1.2 and only the CERN version and this and that and the other, which is what we run for the tier 1, and then they said, no, but this software runs on Windows. Okay, and this is a problem. So we added some nodes, but of course not as many as the 4,500 cores that we run for the LHC. Okay, so this has been, it took us some years to develop it. So it's close work between these sort of PhD engineers, IT experts, and the medical researchers to get something that they actually have managed to say that they actually like it. Okay, and that they're happy with it. And to get a doctor researcher to say that is a great accomplishment, believe me, okay? They're very tough customers. Now we've been running it for 4 years against our cluster. Now it's not exactly all LHC technology. What's LHC standard is the worker nodes, as long as the software runs on Windows. We don't use all the heavy, tape stuff and so on, because the data is not big enough. It's all built on sort of standard stuff, Apache, Tomcat, HTML, so on. It's not gridified because it was not needed, not because we're against the grid. It's just simply that we didn't need it. Okay. And what we see is that there is a very strong peak and valley, okay, because basically it has to do with the added value, okay. Basically, one of these jobs, it would take 2 or 3 days of CPU to process one image, okay. Now, the typical data set that would be useful, that you tell them, what would you really like to have for your experiment? And you could accomplish it for example, in the Barcelona metropolitan area. Because, of course, you have to find people who are willing to be scanned. Some are controlled, so they're healthy people, but some have to have the disease. Not everybody wants to be a volunteer or whatever. But they say 200 would be the ideal, because then we would have statistical power. Okay. What's the typical data set size? 40. Why is it 40? Anybody guess? It's barely enough statistically. It doesn't let you check any systematic errors. Okay, so that's a problem. That's why you would like 200. Okay, but there's another answer, and the answer is that 40 times 3 days of processing per which one is 120 days, which is 2 months, which is the limit of patience that the doctor has before he knows or she knows the results of the research. Okay. Now, we do that in 1 weekend. Why? It's very simple. The success, as it says here, is that we have some fluctuations. We cannot keep such a large cluster always full. So by grabbing 2 to 4% of the cluster, okay, especially with a customer which, when they come in and you give them the answer very fast, then they go off and think for a few weeks or maybe even a few months, so you don't see them very often, so they don't bother you very often. But they're very happy because they have actually managed to get the answer before they forgot what the question was, you see. Because this is the problem. If you wait 2 months for your processing, yeah, you have forgotten what the hell you were doing. Because these doctors are very busy people because they have another life where they're not researchers, they're taking care of patients on an everyday basis. Okay, so I think you get the picture. So why am I here? Okay, well, because we need to run on several operating systems. We don't always can work with even the Linux versions. We need access to GPU-accelerated nodes, and I cannot justify buying a whole cluster and keeping it just for this project so that they use it, We would go backwards to the, I can only buy 2 nodes of GPU-accelerated, okay? So put them under your desk, and maybe in a few months' time you will have the results, okay? So what we need is cloud, okay? We need to provision very rapidly. Also, we could even access perhaps Windows nodes or things like this, okay? And also, we see some advantages because of data sharing, for example. Right now, this data is kind of trapped, I'm the researcher, I take my data, I process it, I publish, I get the results, I publish, and that's it, okay? But it turns out, when we talk to the developers of the software, curiously, these are people in electrical engineering departments or computer science departments. They're not linked tightly to the medical research community. And they often say, do you have any data sets, maybe 10 or 20 images that we could have to test our software? Okay. So curiously, we are actually a test site for the MIT GPU acceleration, okay, with our lousy 4 nodes that we have with GPU acceleration. But why? Because we can run the jobs automatically and give them back the results. Okay. Now, could we now sell access to this data, okay, for other purposes and so on? So think about it. There are many, many possibilities. Also, finally, of course, we need to move all this into a commercial environment. Doctor researchers are actually quite used to paying for things. For example, they actually pay themselves in some sense, or they pay the hospital for the use of the scanner. Okay, by the way, one scanner typically can be several hundred euros. Okay, so this is just for the use of the machine. So they're used to that. So they don't mind, let's say, if the processing had to be paid for. But you need to have a scheme, and they need to see an added value over the graduate student running the jobs under the desk. Okay, and I think we have now broken this barrier. We have a set of people who are high-level researchers who can testify, yes, this is a better way. So they've become believers. Okay, and of course, the idea would be eventually that the pharmaceutical people would jump on board, and then it's big business. The rest is written in our proposal. So because I've run out of time, let me just be very quick. We have not quite an SME, but we have set up a non-profit organization in order to be able to start discussing with the private sector on how to transfer these technologies. We have a stable relationship with the algorithm providers, both in Europe and in the United States. And we have data providers, mostly in the Barcelona area, but we're also discussing how to go. Now, before we said 40, then we said 200, but what about 2,000? Would that be interesting? The answer is yes, in some cases it would be interesting, because 200 would not be enough, because there is I don't know, genetic variations and gender variations and this and that. The problem of 2000 is that you cannot do it in a single metropolitan area, so it cannot be done in a single machine. So now we need a collaboration across Europe, for example, in different places, and we need the collaboration of the manufacturers of the machines in order to intercalibrate them. They would be willing, okay, but we need to set up the environment for them. Okay. So anyway, you probably want to know about the market. We estimate that there are 5,000 such projects active at any given time in Europe, okay? So one work unit, so one of these data sets that gets run is 2,000 hours on a standard CPU, or 1,000 if you have GPU accelerated code. Data is not very much, it's 7 gigabytes, maximum of 60 gigabytes of output, so it's not very much by LHC standards. You rerun it, you should rerun it several times to study your systematic errors. Many people don't because it's such a pain, okay? But now multiply that by 5,000. It turns out now you're delivering 100 million hours of CPU, okay? Sounds interesting, no? Okay, there are licensing aspects, there's the applications themselves. Some of the applications are actually written in MATLAB, so that's another one of our problems. We have a limited number of MATLAB licenses that we can afford. And of course, the GPUs as well. Okay, the motivations I think I have touched on, but it touches on many things that have been said. For example, the secure access, you know, of course, medical data, even if it's de-identified, you have to be a bit careful. Scalability of resources, and also we want to build a financial model, okay? And there, because of this very, very peak, long valley structure, we want to compare whether we should leave the data in the cloud, because of course if we leave it in the cloud, you will charge us, okay, every day. Now it depends what you charge us, and what you charge us for getting the data in and out, and also whether the in and out, although what I heard about Jean, so that's good news, that maybe we could ingest the data fast, okay? But if it wasn't fast, then of course that would slow down the whole process. So we want to compare these two. Okay, so by the way, I had put the word cloudification, and I didn't know that you were going to say that, okay? So, so the objectives I think I have made clear. And so as a summary, this research is important. It's important to accelerate it because this will have an immediate benefit for society. The key factors: turnaround time, access to variety of environments, and reasonable cost. And of course, that we can stop depending on somehow the charity of a tier 1 LHC cluster, and that this thing can sort of be on its own and on a commercial basis. And we're ready if you're ready. Thank you very much.
Are you going to take questions?
Yes, yes.
So I'm a doctor. I have these 20 or 40 or 200 images, and I run them against one of the algorithms. Do those images then become available to another doctor to run against another set of algorithms?
Currently not, but currently not because there is no, it's so awkward for them to ship. I mean, to them data is practically immovable, okay? But we could set up a kind of, call it a marketplace, okay? In fact, by the way, this is MRI and PET brain studies. Mm-hmm. But this is only the tip of the iceberg, okay? There are videos of hearts, okay? There are mammography. Mammography is a huge market, okay? Which automated detection of microcalcification. I mean, this is huge, okay?
Venous ultrasound and,
yeah. And so on and so on and so on. And in fact, talking to my mammography colleagues, because it turns out our institute also develops CCDs for digital mammography as a byproduct of Atlas pixel detectors, it turns out. And they tell me that we should have contests. We should put 1,000 mammographies out there and challenge people and let them run their algorithms on it and see who can detect more microcalcifications more accurately and just open it up. Okay. There is, I mean, the opportunities are enormous for data sharing.
Well, the
But
only
you have
reason
to
I
make it
raise that
easy.
is because it answers your question, should you leave the data there? If leaving the data there adds value to other downstream processors, then there may in fact be no cost for leaving the data
Absolutely.
behind.
That's a great observation. That's a great. It could be self-financing, in fact. If you could, it's sort of like putting ads on your webpage, right? So yeah.
So at the moment, the total size in number of images that you have available.
Okay, we have supported over 4 years something like 25 projects. Okay, whose typical image size is this 40. Okay. The exceptions to the rule have been one project, which is this 200 level project. Okay, and above that there is nothing. Okay, except there's a few projects, mostly in the United States. How do I say this diplomatically? You remember what I said about you should intercalibrate your machines before you scan people in different places? Well, they've learned a lot about that.
Yeah.
Okay, so one of the things that actually should be done is, if ever, I hope, I live to see it, we actually can set up, for example, a Huntington's disease or a Alzheimer's disease, European-wide study with 2,000, 4,000, while the data is being acquired. Okay, because I'm talking about 2,000 subjects, but think about it, you have to scan them every 6 months, okay, and do this for 4 years. While you're taking the data, you should do quality control. So you should ship it somewhere, process it, and check that this data is actually compatible, okay? Just like these beautiful deformations, I mean, how you must always check that it's all calibrated and that suddenly Rome has not sank by a meter, okay, because then obviously something is wrong. So this is another thing, is that people are very reluctant to do quality control because they say, oh God, another 6 months of processing and I will get nothing except quality control out of it, okay?
Last quick question. Do you have any awareness, contact, or exposure to the new grid infrastructure for neurodegenerative disease? No.
Yeah, I mean, we are aware of some of these things, but we've sort of started from the other end of things, okay? So it's not how do we get grid or how do we get neuroimaging on the grid, but our model is something called the LONI at UCLA, okay, which is the Laboratory of Neuroimaging.
They made, in fact,
okay.
The new grid group is also in collaboration with LONI and C-Brain infrastructure.
And the difference is that we think that this should be a much more open platform and more easy to use. I think all of these efforts are complementary, okay? And they also have started in different time frames, okay?
I was wondering if at a certain point is planned to have sort of collaboration, at least in the data layer, let's say, having more images.
I mean, we can discuss, and maybe we can discuss later in the cocktail, okay?
Any other question?
I might have missed it. I saw some numbers in your presentation, but what is basically the steady flow of images that need to be processed currently under the PIC software as you're running it? And what are your projections, if it would be on cloud, where it could go to?
Yeah, well, you got to think that PIC is very small because it only handles data currently from the Barcelona metropolitan area, okay? So, I mean, it's even a bit artificial to talk about a steady flow. I mean, we support something like 5 projects simultaneously, okay? So, let's say every week somebody does one of these flashes in the cluster, okay? That's why, in some sense, we don't see it, okay? But the important thing is that you gotta understand that all of this research is basically self-inhibited by the incorrectly perceived barrier that the processing is a barrier. Okay, I mean they've created this because they've only had the two PCs. Okay, now if you remove this, okay, then they suddenly say, oh, we need to compare the different softwares. You know, because if I reach a conclusion with this software, I mean, I've seen cases where the two softwares give you a completely different answer, okay? And you need to go back and ask, hey, what's happening here, okay? Or you need to start doing much more sophisticated things. For example, the shrinking of the hippocampus in Alzheimer, okay, is done in an extremely crude way. You basically cut the hippocampus in two sides and you compare the volume here and the volume there, okay? Now, if you could actually fit a surface to this and actually calculate the volume, and if you could actually fit the surface and look at the wrinkles in this, but that would take you probably 1 week of CPU time to do this, okay? So the potential is great, but you need to remove this psychological barrier. So market today, 0. But the plot is exactly like the EMBL plot, okay? Market 5 years from now, exponential. My opinion. Huh?
No more questions? Si.
Hi, Steve James from Logica. Is the software, though, currently designed for that kind of scalability on a cloud-like environment?
Yeah, because the software, you mean our control software or the application software?
Application software.
The application software. The application software is basically embarrassingly parallel processing. So, you know, one processor has no idea what the other one is doing, okay? It's technically imaginable to actually parallelize it and run it, let's say, on the MPI and so on, but really there are no benefits, okay? No particular benefits. Now, maybe if we were to do very sophisticated algorithms, then that would be a different story. So basically, the scalability is the same as the Atlas use case, is basically embarrassingly parallel computing. So there is no limitation. We've never seen one. So.
You mentioned momentarily ago about the time period moving up to a week. But of course, a cloud wouldn't necessarily help you unless you could scale that in a parallel way. So is this a job, multiple jobs then, or still one singular?
You're right that it would lengthen the processing if the algorithms are, so there is where maybe GPU-enabled nodes would or you would be forced to go into multi-node provisioning and running, and there, of course, what's inside the cloud becomes less transparent because, of course, we all know you cannot run parallel jobs across arbitrary cores. Okay, so yeah. Now the grid has actually demonstrated that you can schedule. I mean, the EGI grid can schedule MPI jobs correctly. Okay, so I mean, it's a technical, let's say, more of an issue than a challenge, I would say. Okay.
Yeah, so there may be some evolution to the software or innovation within the software as well as innovation within the hardware arena.
Yeah.
Yeah. Okay.
Yeah. Yeah.
So
Yeah, and I think, sorry, it's just because I think one of my sort of flashes for the future, not too long future, is that we will have a general cloud, you know, so running, you know, x86 processor or whatever. But I think there will be a niche market for sort of specialist, you know. I mean, think about it. You know, gravitational wave research uses enormous clusters with GPUs. Okay, every single machine with a GPU, 3,000 nodes. Okay, at Hanover, for example, you can go see it. Okay, so these kind of specialized providers, you know, or parallel job providers.
Manuel,
Yeah.
Nice presentation. I'd like to ask you about MATLAB. You mentioned MATLAB.
Yeah.
Did you have the chance to talk to MATLAB or to understand their their concept of implementing their software in the cloud?
Yeah, I'm kind of the wrong person to ask because in previous jobs that I've had,
I know.
I've had dealings with MATLAB, and and they were not very pleasant. So let's say this time I have not even tried.
Well, it could be very interesting.
Yeah,
I mean,
yeah,
it is.
but I think some of the in EGI maybe people were discussing about flexible licenses and whatever. So I was just kind of hoping that somebody else would solve that problem for me. You know?
I mean,
And in fact, that's another motivation for being here and for proposing, because you know, if I have to solve all of the problems surrounding this, you know, it will take me forever. But if we're all solving different problems, you know, then we will all help each other.
I agree. I mean, MATLAB is definitely is an expensive package, but on the other hand, it's a very widely used in science package.
Yeah.
And using that in a cloud could definitely be very interesting.
Yeah, and the kind of gold standard software in this field, unfortunately, was started with MATLAB, and it keeps continuing developing, and there is no expectation that it will ever abandon MATLAB. Okay, and so they have so much software built up, and they're the gold standard. So you know, we won't get rid of it. That's for sure.